Hey class, Mr. Moydian here with another introduction to understanding similarity in geometry. Hopefully you saw from the last video, the one that the other person made on the grid, that similarity deals in part with proportion and proportional relationships and growth in a coherent way so that everything grows in the same manner so that you don't have distortion. So figures are similar if they are proportional. That's one way to think about it in a broad sense. So here I've given you two pairs of shapes. Let me kind of separate the worlds here. And the question is, are they similar? If they are, then we can notice some numerical relationships about their side lengths and their angles. So let's observe first of all that in this pair of trapezoids, so we're looking at the right hand side first, in this pair of trapezoids the angles that correspond are all congruent. So this angle and this are the same in the baby shape, but it's also the same in the larger shape, and they're all four single stripes, or they're all the same and similar for the double stripes. So that's good. All four angles are matching, and that's the case in the rectangles too on the left hand side of the screen, but I'll tell you right away that only one of these pairs represents similarity. So let's find out which one it is. So angles is not sufficient, at least for this kind of shape. So in the baby shape I have a 4 right here on the bottom. Well, hopefully you can visualize that if these shapes are similar, there was a rotation or a reflection, depending on how you look at it, but also a growth of some kind, right? So the question is, how much did it grow by? And some people might think, well, 24 is 20 bigger than 4 is, so maybe I just add 20. But adding here is not going to give you coherent growth, and I'll give you a vivid example of that. 2 plus 1 would give you, this is not, you have to write this down, 2 plus 1 is 3, which is a lot bigger than 2. If you think about it in relative terms, it's almost half as big as 2 is. But, something like, 100 plus 1, well, 101 is basically the same as 100. So proportional growth doesn't deal with adding, it deals with ratios, and ratios in turn deal with parts and wholes and relationships. So going back to this topic here, 4 must multiply by something to give me 24. Well, the way to solve that is simply divide the old by the new, the new by the old, and you get 6. So multiplying these matching parts seems to be a scale of 6. Is that remaining throughout all the other side pairs? Well, let's find out. Let's see, this pair here, which is 3, it comes up over here. Well, 18 divided by 3 is, what do you know? 6. And same thing over here with this 3 and this 18. So 18 divided by 3, what is that? It was also 6. So far looking pretty good. And the short base here, this is 6, and it appears to become 36. I think you can probably figure out what's going to happen. 36 divided by 6 is 6. So are these two shapes similar? Let me choose a better color here. Yes, they are. They are similar, and these equal ratios are proof of that. Let's take a look at the rectangles. Oops. So all 4 angles are the same, and they're all 90 in this case, which is nice. So keep in mind that that's also in common with the trapezoid, so maybe that's enough information. Now let's figure out exactly what matches. Notice that 36 is the smaller of the two sides, so this is kind of hard to visualize, so let's just use bigger versus smaller to help us here. 36 is the smaller of the two, so if these are similar, we know that it can't match with 35 because that's the bigger of the two. So if these are similar, then these need to be buddies with each other. I'll just use the same color because they're the same length. And likewise, if they are similar, then this 60 should match with this longer side, which is 35, right? The question is, do they match up in this way? Let's find out. So the shorter sides, it is currently 30. If you look at this as the new shape, 30. It used to be 36. That's not quite as neat as the last fraction, but that would reduce if you divide both by 5, just some simple 4th grade math, and you get, let's see, 5/6. So this length in yellow is 5/6 as long as it used to be. Obviously this picture is not drawn to scale, just using the numbers as a relationship here. So the question is, do the purple sides also share that pattern? Well, let's find out. Let's see, I went 30 over 36. That would be the smaller looking shape divided by the older one. So keeping that same proportional relationship, that would be 35 over 60. Is that 5 6? Well, 35 is divisible by 5 and you get 7. 60 divisible by 5 and you get 12. So that ratio of the purples is a 7/12 ratio. These are not the same as they were 6 in the trapezoid case. So are these two rectangles similar? No, they are not. So hopefully you recognize the importance here of part versus whole, and also beginning and after, and maintaining proportion and maintaining order. So just looking at the relationships there. So here I gave you two shapes and I asked you, are they similar? Here I'm telling you, hey, here's two shapes and they are similar. So this symbol you haven't really seen before, but it looks a lot like the congruent symbol minus the equal sign that lives underneath it, just a squiggly. So the squiggly there means similar. So it's a symbol that means similar. So you're given that these two shapes are similar, and the question is find x. Okay, well, let's see here. We got to be careful about orientation. So it looks as though the small shape sort of rotated and then also dilated to become the larger shape. So what that means is AB, which is sort of on the top here, corresponds to let's see, DE, right? In fact, you can see that by the name, AB and DE. So if these are similar, and we're told that they are, then we know that the ratio should be x is 12. And so I went from small shape to large shape to get that fraction. Similarly, BC should be the same as EF. Well, EF is 9. So small shape to big shape, that would be 3 is to 9. So the yellows are in this proportion. We don't know what the x is. The reds are in that proportion, which is 3/9. The question is, what is x? And the reason I know that I'm allowed to do what I'm about to do, which is put an equal sign here, why is this true? It's because we are given that they are similar. So we're allowed to put the equal sign there because we know that they have to be proportional. That's how we were able to verify similarity on this slide. So here we have a missing piece. The question is, what number does it need to be for it to really be similar? Well, you might remember a common technique, and it's one that I'm a big fan of in some cases, which is called cross multiplication. So it's something a lot of people remember from middle school math, but it's a useful tool when you have two fractions and when they have certain criteria. So cross multiplication ends up being useful here. What you have is 9x for the one diagonal, and the other diagonal would be 36. So there's our equation, and it's very easy to solve, and you get x. 36 divided by 9 would be 4. So now we know that this number here must be 4 in order for it to maintain the proportions which it needs to be similar. So x equals 4. So keep this in mind, that I'm giving you a pair of similar shapes. The question is, what number is required to maintain similarity? Contrast that here. Here are the numbers. Do they have similarity? Do they have equal proportions? And here, how do you find equal proportions? Finally, I want to close with another perspective on similarity. We'll talk a lot more about similarity in class. So some of this is a little abstract. Don't worry, we'll make it more concrete in class. So here you're given two shapes. It's dilation. So you're told, wasn't able to write down all the steps here, but you're told that the small shape, which is a rectangle, technically without the angles we don't know that, but let's just see that it's a rectangle. And it's dilated by a scale of 3, scale factor of 3 to make a new rectangle. Well, right away we know, hopefully, without too much of an effort, and just somewhat by early levels of math, that if the scale is 3 and this is 4, then this, therefore, 4 times 3 would be 12. And likewise, if this side here is 2 and the scale factor is 3, then this side over here becomes 6. The real question, or the real concept that I want you to think about here, and it's not really a question, just something to visualize and ponder, is what is the scale for the area? Or to put it another way, how many of these will fit in here? And the answer is not 3. You might think it's 3 because, the scale is 3. But think carefully about what we're doing. We're stretching the 4 to become 3 in the horizontal direction. We're also stretching the 2 to become 6 by multiplying by 3 in the vertical direction. So we have 2 dimensions of stretch. So the 3 really is going to become into a different number. So here's how we can really visualize that. I'm going to try my best to pick this thing up. I don't know how well it'll show up on the recording. So I'm going to pick this up and I'm going to move it over here. All right. And let's see if I can get this thing to work properly. So copy. I'm actually just going to paste it. That might be easier. So there's one. Paste again. There's two. And there's three. So three will fit along that's, horizontal length. Similarly, 3 will fit, if I proportion this thing right, in the vertical direction, because we stretch in both directions to maintain proportion. So if 3 fit horizontally and 3 fit vertically, I don't think you have to really see it all done, but hopefully, I'll just go ahead and do it because it'll complete the picture here. If you're at bigger numbers, you can't really draw all of them. You can just take the shortcut. You can see that 9 of them, not 3, will fit. So a scale factor of 3 leads to a scale of 9 in terms of the area. So we can actually see that numerically too. The original area of this shape is base times height, that's 8 square units. Right? So a scale factor of 3 might make you think, oh, okay, 24 square units. But see, no. This is 12, right? Before all the stuff covered it up. And this is 6. And base times height here is base times height, which is 6 times 12, which is 72 square units. And this is a lot bigger than 3 times. Right? 8 times 3 is not 72. 8 times what is 72? 9. And that's because 9 of these will fit in the original shape. So in general, if your linear scale is a number, then the scale of your area will be the square of that number. And the reason that it's squared is it goes in both directions, horizontally and vertically, to maintain proportionality. Alright, I went a little bit long on this video, longer than I intended, but hopefully you have a better sense of the importance of proportions in similarity. Alrighty, see you in class.